Well, here we discuss first countable topological spaces. So recall that. Okay, so this is the outline of today's lecture. First, we define first countable topological spaces. Then we will characterize closed sets and continuous functions in terms of first countability. Okay. Well, uh, you know what is definition of a basis of topology. Uh, Recall that. Let X tau be a topological space. Then a subcollection script B of tau is called a basis for the topology tau if for every open set U and X belongs to U, there exists an element in script B, let us denote by B, such that X belongs to B and B is contained in U. So that is the definition of a basis of the topological space X, tau. Now for little x in the topological space X, a basis of the topological space X at the point X, that is local basis, is a collection of open subsets of the topological space X containing collection of open subsets containing X, little x, such that if U is any open subset of X then containing X, then there exists an element in the collection such that that element contained in U and it contains X. Okay, so more precisely, let X tau be a topological space and X belongs to X. Then what is local basis at X of the topological space X, tau? That is a collection we have denoted by beta X of open sets of tau such that for every open set U in X containing X, there exists an element B in this collection beta X such that B contained in U. Okay, this is local basis, and if this is countable, we call this is countable basis at X. So this is the definition of countable basis at a point. Well, so we say that X, tau has a countable basis at the point X if there exists a countable collection beta X of open sets in the topological space X such that for every open set U contained in X there exists an element B in beta X, and that is open neighborhood of X such that B contained in U. For example, if you take any metric space tau d, that is any metrizable topological space whose topology is induced by a metric d, then for little x in X, consider the collection beta x equal to set of all open balls B centered at the point X and radius 1 over n, where n belongs to the set of all natural numbers. So this is a countable collection. This is a countable collection of open sets in the metric space. And so beta x equal to set of open balls with centered at X and radius 1 over n, where n belongs to the set of all natural numbers. Okay, then this is a countable collection of open sets. And you see, if U is open in the metric space X comma D containing X, then by definition of open set there exists some epsilon greater than 0, such that the ball epsilon real number, positive real number, such that the ball B with centered at X and radius epsilon is contained in U. Okay, and by Archimedean property there exists some natural number 1 n in set of natural numbers such that 1 over n is less than epsilon. So b x 1 over n, that is the ball with centered at X and radius 1 over n, is contained in b epsilon x, that is a ball with centered at X and radius epsilon. And you know, the ball with centered at X and radius epsilon, that is contained in U. So we have B, the ball with centered at X and radius 1 over n is contained in U, and that contains X. So this proves that the collection beta x is a local basis at X. Okay, so and this is countable. So every metric space, okay, so for every metric space or every topology metrizable topological space, so at every point little x in the metrizable topological space X, we can have a countable local basis. Okay, so this is the definition of countable basis at a point. Now we define first countable topological space. So a topological space X is called first countable if X has countable basis at every point X in the topological space X. So already we have given example. Every metric space is first countable, or every metrizable topological space is first countable. Well, so here we have examples. Rn with Euclidean topology is first countable, and this is recall. This is spelling mistake. A topological space is called metrizable. So this is the definition of metrizable topological space. A topological space is called metrizable if its topology is induced by a metric D on the space X. So already we have explained that a metrizable space X is first countable, and this is a countable basis at X. So Bx, this is equal to the ball with centered at X and radius 1 over epsilon, and this is ball with respect to the metric D. Okay, This is the notation of ball with center at x, radius 1 over epsilon with respect to, and this is the ball with respect to the metric d. Okay, so this is countable basis at the point x. So now r omega, this is r omega is a countable product of a real line r, and with uniform topology satisfy first countability axiom. So recall that its topology, uniform topology, is induced by uniform metric, and uniform metric is given by rho x comma y. So well, x and y, these are points in r omega. So basically x and y, these are sequences. X equal to xi, I belongs to n, and y equal to y, j belongs to n. So this is equal to supremum d xi comma xj for I comma j belongs to n, where this is d xi comma xj, this is equal to, so dx comma y equal to minimum of x minus y comma 1. So this is standard bounded metric on R. Okay, so all these topological spaces, these are metrizable. So these are first countable topological spaces. Well, now we characterize closed sets in terms of first countability. So let theorem 1 says that let X be a topological space and A is subset of X if there exists a sequence X and n belongs to set of natural numbers. So if there exists a sequence in A, that is xn belongs to A for every n in n natural numbers, for every natural number n. So if there exists a sequence in A with limit xn as n tends to infinity equal to x, then the limit of the sequence is in the closure of A. Okay, and converse of 1, this is true if x is first countable. Okay, now what is the converse? The converse is following: if x belongs to closure of A, then there exists a sequence in A that converges to the point x. So this is the converse. Okay, so first we prove part 1, that is suppose x belongs to x, and assume that there exists a sequence of points in A such that limit xn as n tends to infinity equal to x. So what to show here? Here we have to show that this limit belongs to A closure. That is, we have assumed that there exists a sequence xn in A with limit x. So we have to show that the limit x belongs to A closure. Okay, this is very easy. So to show x belongs to A closure, we have to show that for every open set, so U containing x, U intersection with A is non-empty. This is what we have to show. So suppose U is an open neighborhood of x. This is some arbitrary open neighborhood. So by definition of convergence, for this open neighborhood of x, there exists some natural number n such that xn belongs to u for every little n greater than equal to this n. Okay, so this is by definition of convergence of a sequence at a point x. Okay, so therefore, and this xn belongs to a as well. Therefore, for every n little n greater than this n, xn belongs to u and a. So this is non-empty. Therefore, x belongs to a closure. So x is a point in closure of a. Now we prove part 2. So here we have to. So here our assumption is following: x is first countable and x belongs to a closure of a. So we have to show that there exists a sequence xn in the set A such that limit xn as n tends to infinity equal to x. So so basically we construct such a sequence. So here we have a topological space X which is first countable. So there exist. So for this little x in a closure, that is also point in the whole space X. So for little x belongs to X, we have some countable basis, local basis at the point X. Okay, so suppose so this is bx equal to un, n belongs to set of natural numbers. This is a countable basis at x. So existence of such a countable basis follows from, so our assumption that the topological space X is first countable. So we can consider some countable basis at the point X. Okay, so now we construct a sequence. Xn in the subset A. Okay, so for n equal to 1, we choose x1 belongs to u1. So and also x1 is a point in A also. So why there exists a point x1 in u1, that is also a point in A, because see x is what x is in a closure. So if this is if this is countable basis at x, that means x belongs to un for every n, and so u for in particular n equal to 1, u1 is an open neighborhood of x. Therefore u1 intersection with a, that is non-empty. Therefore there exists an element x1 in u1 that is also in a. Okay, then for n equal to 2, we choose x2 from u1 intersection u2, and that is also in a. Okay, so again you see u1 u2, they are open neighborhood of x, and therefore their intersection is also open neighborhood of x. So this is u1 intersection u2, this is an open neighborhood of x. So u1 intersection u2 has non-empty intersection with a, therefore we can choose an element x2 from u1 intersection u2, which is also in a. And in general we choose xn from intersection ui equal to 1 to n, and that such that xn is also in a. Thus we have constructed sequence xn, n belongs to n, sequence in the set A. Now our claim is limit n tends to infinity xn equal to x little x. So to prove this claim, suppose u is an open set containing x. Okay, so u is open set in a topological space x containing x, that is u is any arbitrary open neighborhood of x. So by definition of local basis, we have some element, let's say there exists some element in in the local basis bx such that x belongs to and contained in u. Okay, so that is the definition of local basis. Now one can see that for every n greater than this m, we have xn belongs to the intersection ui I equal to 1 to n. So here in this ui's, so as m is less than n, so is for I equal to m, is there, so this intersection is subset of Okay, so xn belongs to, so by definition of the sequence xn belongs to this intersection, and this intersection contained in okay, and is contained in u by the definition of countable basis, so local basis at x. Okay, so therefore for every small n greater than or equal to big M, u contains xn, and this is the definition of limit of a sequence, and this implies that limit xn n tends to infinity equal to x. So therefore we are done. Okay, so what we have shown, that if x is first countable and x belongs to a closure, then there exists a sequence in A such that limit xn as n tends to infinity equal to x. So that is, there exists a sequence in A that converges to little x. Okay, so here maybe I'll give an exercise. So you may write the exercise. So if x is first countable topological space x, then for every x in x there exists a countable basis b equal to Vn, where n belongs to set of all natural numbers such that Vn plus 1 contained in Vn for every n belongs to natural number. Okay, so this is an exercise. Okay, now theorem 2, this characterizes continuous function sequential criteria for continuity. Theorem 2 says that let f from x to y be a function where x and y, these are topological spaces. Then if the function f is continuous, then then for a sequence xn that converges to x, that is limit xn as n tends to infinity equal to x, this implies limit f of xn n tends to infinity equal to f of x. So xn converges to x implies f of xn converges to f of x, and converse of this is true if x is first countable. So well, this is basically sequential criteria for continuity. So yeah, this is theorem 2. So basically theorem 2 says that if f is continuous, so the main part is the converse one. First part holds true for every topological spaces x and y. If f is continuous, then for a given convergence sequence xn converges to x, f of xn converges to f of x, and converse is true if f is first countable. Okay, so in the first part, let us prove the first part first. We assume that f is continuous and xn is a sequence, convergent sequence with limit little x. Okay, so what we have to show? We have to show that f of xn limit n tends to infinity equal to f of x. Okay, so f is continuous means for every open subset of y, f inverse of that open subset is open in x. So basically for v open in y, okay, f inverse of v is open in x. So let v is open neighborhood of f of x. Okay, that is v is open subset of y containing f of x. Then by continuity of f, f inverse of v is open in x and x belongs to f inverse of v. Therefore f inverse of v is an open neighborhood of x, and our assumption is xn is sequence with limit x little x. Therefore by definition of limit there exists, so limit xn as n tends to infinity equal to x, this implies there exists for the open set f inverse of v, there exists some natural number, this big M, such that xn belongs to f inverse of v for all little n greater than or equal to m. That is, the sequence is eventually is in f inverse of v. Okay, now so we have f of xn belongs to v for every n greater than equal to big M. Okay, from here we have f of xn belongs to v for every n greater than or equal to big M, and this implies limit f of xn equal to f of x as n tends to infinity. Okay, so yeah, the first part is very easy. Now for the second part, so what is the second part? Converse. So here our assumption is x is first countable. Okay, so So our assumption is first countable and x is first countable, and xn limit xn as n tends to infinity equal to x implies, so f of xn as limit n tends to infinity equal to fx. Okay, this is our assumption. So we have to show that f is continuous. Okay, this is the converse. So basically, we assume that x is first countable and f of xn converges to x implies f of xn converges to f of x. Then to show that f is continuous, so we use, so here we show that for every subset A of x, f of a closure is subset of f of a closure, f of a whole closure. So that is the equivalent criteria for continuity. You can go back and see the characterization theorem for continuity. So recall that let x comma y be topological spaces and f is a function from x to y, then the following statements are following statements are equivalent. I am reading the characterization theorem. So the following statements are equivalent. What are the following statements? First one is f is continuous. Second one is for every subset A we have f of a closure equal to f of a closure equal to f of a whole closure containing f of a whole closure. And the third statement is for every closed set B contained in Y, the inverse image f inverse of B that is closed in X. And the fourth statement is for every x, little x in the topological space X, and every neighborhood V of fx, there exists a neighborhood U of x such that f of u contained in V. So this is the characterization theorem for continuity. So here to show that f is continuous, we will show that f of a closure equal to f of a whole closure. So f of a closure contained in f of a whole closure. Okay, so this is equivalent to f is continuous. That is, for x belongs to a closure, we have to show f of x belongs to f a closure, f of a closure. So okay, so this is what we have to show. So if x belongs to a closure, by first part, so by theorem 1, there exists a sequence xn in S that converges to this little x. Therefore, from theorem 1, we have there exists sequence xn in the set A such that limit xn as n tends to infinite, that is equal to x. Okay. So this is sequence in A. Therefore, f of xn, this is sequence in f of A. And by hypothesis, xn converges to x implies f of xn converges to f of x. This is our hypothesis. Okay, and the sequence. So here we have sequence in f of A with limit f of x that implies f of x. This is in f a whole closure, and which is what we want to prove. So this is the converse. So in theorem 1, note that this theorem we have already seen in metric spaces. So in metric space, so what was the statement? So uh, X is in A closure if and only if there exists a sequence in A that converges to X. And for the converse part, so first part is a similar proof, and for the converse part, that is if X belongs to A closure, then there exists a sequence xn in A that converges to X. This is the converse. To prove the converse part, we construct a sequence xn by following xn belongs to the ball b 1 over n x, that is open ball with center at x and a radius 1 by n, intersection with A. So take xn from A intersection with open ball with center at x and radius 1 by n, and you see the distance from x and xn, this is less than 1 over n, therefore distance decreasing as decreases to 0 as n tends to infinity. That's how we construct. So that's how we construct a sequence in A that converges to the point X. So this is the idea we have used in metric space. So this here we have similar idea. So basically here we have similar idea. So here Bx, this is countable basis. So there, so in case of metric space, un equal to ball with radius 1 over epsilon 1 over n with centered at x. Okay, so automatically in the case of metric space, automatically this un are nested sequence of open neighborhood of x. But here but here it is not necessary that this collection un, these are nested sequence, this is nested sequence. That's why we construct the sequence by following x1 belongs to u1 and x2 belongs to u1 intersection with u2. You can see that u1 contained in u1 intersection u2 and so on. Okay, so that's how we construct another countable basis at x that is nested. Okay, and we construct sequence in a similar way. Now I'll ask to show that this condition first countability on x that is necessary for the converse, that is find some counter example. So that is find some example when x is not first countable, then converse is not true. Okay, this is it for